have our next speaker. Karthik is going to talk about sampling and scoring rules on manifolds. And it is going to come up. 1 second. There we go. Okay. Perfect.
Okay, thank you for sticking around. I'm fully aware I'm between you and lunch, so I won't belabor my point beyond what is necessary. I'm, in some sense, the outsider for this workshop. I don't work in this area, I'm new to this area. So when I was asked to give a talk, I thought there must be some conflation between what I do and then what is being spoken of here. I work in geometric statistics, so I thought there must be something to do with curved spaces, manifolds, scoring rules. I'll read a few papers, make up a talk, but there weren't any. There were even very few multivariate papers as such. And so what I thought today is basically to speak more broadly on some basic issues if one wanted to define scoring rules on manifolds, and pose the question whether actually taking into account the curvature is in fact necessary, depending on the kind of application one has in mind, or whether it's possible to completely bypass it altogether using some kernels. And then ask the question, offering no answers, whether that leads to something useful. That's the first part. The second part is, well, if you manage to define a score which you like, how would you actually compute it? And because on manifolds, distributions are not commonplace. They're usually defined only up to some normalizing constant. So it's not easy how to compute them. So I will basically comment on these two, but I'll be happy to discuss if there are any further questions. So 2 questions, as I said, I will focus on. Scoring rules can be defined very generally for metric spaces or even just Hausdorff spaces with no metrics. There's very little structure needed to define a scoring rule. You just need a probability measure, and then effectively you're done once you have a function which it satisfies certain properties. And there are, through the week, we've seen there are very many different ways in which you can define scoring rules. So I will ask 2 questions. If the space I'm looking at is a manifold, that is the data lies on a manifold, and it is a known manifold. This is not a manifold learning problem where you don't know the underlying manifold, but this is a known manifold. Then how does the curvature, if at all, influence the performance of this scoring rule and its properties, especially whether it can be proper or, more importantly, strictly proper, if there's any relationship between the two. And then secondly, as I said, how would you actually compute it in practice? So I'll stick to these 2 questions. So here's a slide saying, well, manifolds as representation spaces of data objects are quite natural. Data really, once you get data in practice, it doesn't lie on any manifold, it's just numbers. But it's useful to view them as points on a certain manifold and then define models on these manifolds in order to do inference and prediction. So if you have directional data, then typically you would think as points on a sphere, or if you have a parameter space with unit norm constraints, then it'll be spheres. If you're looking at graph embeddings and you want the distances between the nodes to somehow reflect chances of forming communities or otherwise, hyperbolic embeddings are quite common. We have spherical embeddings as well in machine learning literature. If you're interested in covariance matrices as parameters or just as data themselves in diffusion tensors, for example, then the space of positive symmetric, positive definite matrices is the natural representation space, curved manifold. If you're looking at protein data and then you have vectors of angles in protein bonds, then it's natural to represent them as points on some torus. Or more generally, if you have images where you have objects in them and then you're interested in their outlines. There might be a cell, for example, and then you're interested in the shape of the cell, the outline. Then there would be certain nuisance information, rotations, translations, reparameterizations. And when you take them all out, you're left with some kind of a manifold structure, or at least a non-Euclidean structure. Or what is probably more familiar if you're looking at the space of probability measures, you have the Wasserstein geometry, you have a curved geometry there, or you're looking at the space of densities, Fisher-Rao metric, you have a positive metric. So effectively, there are quite a few situations where a manifold structure is useful to think of either for the data point or for the parameter space. So very quickly, because this will be relevant, positive, zero, and negative curvature on spaces as such, or what I say sectional curvature. Triangles on spheres typically will have angles which sum up to larger than 180 degrees. And you can see why. Intuitively, it's very clear. In terms of straight lines starting off at a point, they will go away and then they'll start eventually converging because the positive curvature brings it down. The opposite happens for the hyperbolic space, which is negatively curved. Triangles have smaller angles. They don't sum up to 80, much smaller than them. But straight lines starting at a point start diverging away. And you can think of curvature in some. The cylinder is effectively flat. You can just sort of cup it open and put it flat on a plane. It's effectively like R2. So the triangle just looks like a usual triangle. So positively curved manifolds are usually compact, not always. There are lots of examples where they aren't, but typically in practice they'll be compact. Negatively curved are usually associated with non-compact. So they can be globally flattened. Positively curved ones, you can't flatten it without distortion of the distances. So that's the main idea which will be required. So I'll look at properties of scoring rules on manifolds and concentrate mainly on kernel-based ones. So what would we want for a scoring rule on a manifold? How would we want for it to behave? So here's a distribution on the curved torus, and we have a point x on the left-hand side, which is lying on the inner side of the torus, which is negatively curved. On the right-hand side, it's the same distribution. You have a point lying now on the outer side where it's positively curved. Now, for the same distribution, you can see that the colors this is the heat map of the densities. So the densities are roughly the same at both sides, on the inner and the outer, but the curvatures are different. Do we want the score to reflect this? Do we care? Or do we just care that the density is whatever it is, if you're looking at a log score? It's not immediately clear what one would want. However, in order to define a probability distribution on a manifold and so on, you have to start off with some kind of a metric. Typically, the topology comes from some kind of a metric. So the probability measure would automatically be adapted to the geometry by virtue of its definition altogether. So intuitively, you can say, well, maybe not. Everything is there in the probability measure. Whatever it says is what is there. Extraneous to that, the actual structure of the space, maybe not all that important. Intuitively, you would think that, and by and large, that's true, depending on what kind of a scoring rule one chooses. So this is a situation where the probability adapts itself to the geometry automatically, in some sense. And you can think of designing scoring rules of that sort. So one way to do that is to look at scoring rules based on kernels on manifold. So I won't belabor the point. These definitions have been used earlier. If you weren't sufficiently confused already, I've gone back to the other way. This is a penalty now. Okay. Lower the score, the better. I've used that definition. And strictly proper ones are those which will actually distinguish distributions, which will separate distributions. Now, one can define a kernel score on a manifold, which will be strictly proper, effectively by starting off with a kernel which is characteristic in the usual sense. that there is a mapping from the space of probability measures to an RKHS space, which will be injective for the given choice of kernel. If one can find such a kernel for a manifold, regardless of its curvature or its geometric properties, then you can define the kernel score in the usual way. It will be strictly proper. You can safely ignore the underlying geometry as such. Of course, you need to be able to find a kernel which satisfies this. And there are positive results in this direction. Johanna has a paper not too long ago. For general compact spaces, it's possible. For general compact spaces, there exist kernels, characteristic kernel, which means I can take a sphere, or I can look at the space of rotations or complex projective, all these manifolds with curvature which are positive. And then if I can find a kernel which will globally just flatten it, even though positively curved manifolds can't necessarily be flattened as such, but as far as the probability measures go, they can be flattened enough to distinguish between the two. So if such a kernel is available, then you can use it. And there are examples already available. There is one particular kernel which stands out because it's different. That's the energy score. If you choose the kernel to be the distance in the Euclidean space, it corresponds to the energy score. And this energy score is actually equivalent or is very closely related to the distance covariance, which is an actual metric on the space of probability measures. And in this sense, in this case, it is a strictly proper scoring rule because it uses the distance directly. So this is a situation where it's not necessarily the case, it is the case that the probability has adapted itself to the flat geometry, but even the converse is true. That as long as I have points and I have distances between them, I can characterize the probability measure completely. That's what this is saying. So the geometry is determining a crucial aspect of this problem if one uses the energy score. And this is quite popular. And it's popular especially if you want to generalize to the multivariate setting or to the higher dimension setting, because you just need distances. So in similar spirit, if I say, well, let me look at an energy score on the manifold, I replace the distance by the geodesic distance, then curvature plays a role and it can't be ignored. It plays a role in the following sense. If the manifold is a hyperbolic space that is constant, negative curvature, -1, constant curvature, but negative, then there's no problem. This will be strictly proper. Okay. You can go ahead and do whatever one wants to do with a strictly proper scoring rule. But positively curved, you need some restrictions because positive curvature brings about some problems. You would have to restrict to a subset which contains at most 2 points which are antipodal to each other. Meaning not a unique shortest geodesic between them. You can't go outside of, if you go outside of this set, then it's not strictly proper, basically. So it puts a restriction, so maybe just a northern hemisphere or the southern hemisphere. Or if you're interested in discrete probabilities, if you take square root of discrete probabilities, you go from simplex to positive orthant of the sphere. So that positive orthant will satisfy this. Yes, that's another way of thinking about this problem. What about negative curvature, which is not constant, but it's changing, but stays negative? It's an open problem. No one really knows the answer to this. However, if you restrict the set of all negatively curved manifolds which are simply connected to those which are symmetric, meaning they're sort of, the curvature looks the same in all directions in a way, then I'm brave enough to make the conjecture that I think it's true. I don't have a proof yet. And an example which will be useful in this setting is positive definite matrices. If you have an affine invariant metric on this, then it's negatively curved everywhere. It's a symmetric space and might be true. Okay. So it's generally an open question. If you want to use an energy score on a manifold, how the curvature plays into the story. It's not clear. So the intuition behind this is the link that strictly proper scoring rule based on a distance used as a kernel is equivalent to the metric space being something called strong negative type. Okay. These are the conditions. This is the definition of a strong negative type. It's an equivalent condition effectively. And Russell Lyons has two papers on this for the sphere and the hyperbolic space, and mentions that it's open in general for negatively curved, which might be changing. Okay, so that leads to the previous conjecture as such. So this is a situation where the geometry actually, as with the energy score in the Euclidean case, the geometry characterizes the probability. So if you want to score based on this, curvature has to be accounted for. So that's the first part. Now I'll just briefly talk about how one might actually want to compute then, once you've taken care of all this and you've defined a scoring rule using a kernel. So you've chosen a kernel. You have either a proper or a strictly proper, doesn't matter. You've chosen a kernel, and then you have written down your scoring rule. But the probability measure you're looking at is one wherein it has a density. It's very difficult to just define abstract measures on manifolds. Typically, you would have some kind of density. You'll start off with a non-negative function, and then you'll have a dominating measure, which is the volume form, and then you'll write it up to a normalizing constant. Unless you have some very nice spherical or something very standard manifold, it's very difficult. So the usual way is to write the measure as a density up to an unknown normalizing constant. So now, if it is of the form e to the minus some potential phi, this phi can be anything. It needn't be convex. So you needn't have to think of it as a log concave kind of situation. It can be very general. It can have heavy tails, it can be polynomially decaying, but it needs to be smooth in some sense. If that is the case, then we can use sampling. We can sample from this unnormalized density on the manifold and then approximate this, and then actually give some theoretical guarantees. This is based on some recent work I've done with my student on how to sample using Langevin dynamics on the manifold. If you're familiar with the Langevin-based sampling on the Euclidean setting, it transfers over almost exactly. You set up a stochastic differential equation, which is a Langevin, but you define it intrinsically on a manifold. There's no need to have it running on a larger space and project down. It's actually running, let's say, intrinsically on the sphere. There's a Brownian motion on the sphere, and then there's a drift for this, which is determined by the potential, the gradient of the potential. So this allows you to ignore the normalizing constants altogether. So this is a Langevin dynamic, and in order to sample using this, you would have to discretize this, take time 0 to t and discretize it, break it into small steps. So you discretize it of fixed, let's say fixed size h, time steps h between size of the grid. And then in the Euclidean case, the value at time n plus 1 would be the value at time n minus something, the gradient direction. The analog of that in the Riemannian, in the manifold setting, is the exponential map, or it's basically saying I'm going to follow the short line, the shortest path from my current value to the next value. Okay. That's effectively what this exponential map is doing. So this is the straightforward generalization from the Euclidean to the manifold setting of the Langevin algorithm. Okay. Now you need to make sure that things don't explode, that you don't leave the manifold and go away, or you have to make sure that this algorithm and the continuous process also mixes nicely, goes around everywhere, so it's ergodic enough, so that eventually you'll be converging to this stationary distribution, which is your target measure. So in the manifold setting, you have to control the curvatures. Okay. Typically, you control curvatures with some lower bound on a Ricci curvature and then on the Hessian of the potential. And these conditions are not very stringent. For the scoring rules, to define proper scoring rules, the conditions are automatically satisfied on manifolds. Okay. So these are not really that stringent as such. So pictorially, this is what is happening. You're at on top, you're at time n, you're at xn. On the tangent space, you choose a particular direction which is driven by the gradient of phi of your potential. And then you go along that, and then you use the exponential map and come down to the next point. But that's equivalent to just going along the geodesic from xn to xn plus 1. So here's a small simulation for how the algorithm runs on the sphere when we want to sample from a 1 Mises distribution on the sphere. It converges fairly quickly. Okay. And the nice thing about this is, of course, you get some theoretical guarantees, which is what I'll talk about. So finally, if you want to approximate the scoring rule, as we wanted to use this, we have a sample from this algorithm, 0 to t, broken up into n time steps, each of size h. We have a sample. We run t is long enough so that the chain is mixed sufficiently. Use the samples, construct the usual U statistic to approximate the score based on sums. And because of the properties of the algorithm, you can give some guarantees. You can give an optimal bound in terms of the step size h and the time t, which is actually the number n times h, the sample size times h. The bias, there is a bias term. Okay, you can get rid of it with the Metropolis Hastings correction, but there is a bias term. And as you can see, as sample size n goes to infinity and h gets smaller, it dies at an appropriate rate. But the mean square dies at the usual rate, as you would think. It's a parametric rate. And this is optimal. You can't do any better than this. Unless you start changing this step size h as you're going down the algorithm. If you're adaptively changing it in some sense, then you might converge better. But otherwise, you can't do any better. So this is a way of computing a kernel-based score on a manifold. You can say, well, I usually get my data. I don't really care where it comes from. It comes from a generative model, in which case, yes. But if you're actually designing the model and trying to implement it and get it and then evaluate its predictive accuracy, then this will be useful. So there are many ways in which you can go. In essence, if you're just looking at proper scoring rules, you don't care about strict propriety, you can largely ignore the geometry for manifolds. You can largely ignore and you can get away with it because the kernels, there are characteristic kernels which allow you to just transfer the problem onto a flat Hilbert space and effectively you're done. But for strictly proper, if you want to use some kind of the energy or something based on a distance, then there's no way out. You have to account for the curvature. You have to somehow control it. You can extend this kernel business to non-Euclidean spaces which are not manifolds, which are like stratified spaces, which have singularities. There are many pieces. Each piece in itself is a manifold, but they're glued together on their common boundaries in some way. A common example in statistics is the geometry of phylogenetic trees on a fixed number of leaves. It's a stratified geometry. This is a section of the space. This is not the entire space because the whole space can't be embedded in either R3 or R4. This is a section of it, and you can see that there are like 5 pieces, and they're glued together by some common boundaries. And this is a metric space. This is cat 0, as they say, which is like non-positively curved. Maximum curvature is 0, which means you'll have a unique geodesic between points. So you can do nice statistics on them. So kernel scores can be defined and on this as well. In general, you can, as was mentioned in the last talk, you can design scoring rules for estimation. In manifolds, the state of the art is to use sample Frechet means, minimizing distance squares, but maybe there are cleverer scoring rules you can use and come up with better estimation strategies. But just more generally, there's much to do. And this is an invitation if you're interested in it. And thank you.
Thank you very much. Do we have questions or comments? Yes, we start there.
Thank you. I really enjoyed the talk. I'm just wondering what you're assuming about scoring rules. Are there any kind of continuity or measurability assumptions?
Measurability, certainly.
And what's the sigma algebra on the space of probability measures? Is it just as minimal as possible, or?
The sigma algebra to define On the probability space?
Yeah. On the space of probability measures, because there's an argument which is a probability measure, right?
Yeah. I mean, you could use any sigma algebra one would use to define probability measures on arbitrary metric spaces.
But, okay, I mean, presumably all scoring rules we'd be interested in would be measurable with respect to all of those different sigma algebras, but
Yes.
a precise, like if you're using results that prove something about all scoring rules, I just wonder whether the measurable, like the technical choice of the sigma algebra would be important.
Maybe. I haven't thought of it. It may be.
Thank you.
Dave?
Very nice talk. For your approximation results, I would assume that the correlation or the dependence in the chain will bias heavily the estimates.
So this is, if you run the chain long enough, if the T is really long, then you know that you reach ergodicity.
But that's not because you're looking at xi minus xj, and if I and j are close, they will be very dependent, maybe. I guess it should depend a lot on the mixing of the chains.
It does. You're guaranteed to mix under those conditions. And in practice, you can actually see that if T is, let's say, 8 or 10, and then you take 10,000 steps, and then you're controlling for all the other things. Effectively.
Yeah, okay. I guess it's kind of, for practical experience, when I've tried this, you need like extremely long chains for this to actually.
I think that's true. That's true. You would need a large number of points. That's true.
And then another small, maybe I misunderstood, but these energy scores are not strictly proper, right? Like a counterexample would be you use the energy score with the norm
They
square.
are strictly proper if you reduce it to, if you choose the exponent.
You use like the norm squared in the energy scores, and you can like.
You can't use norm square. It's strictly lesser than 2.
Strictly less than 2.
Yeah.
Thanks for the talk. I'm not sure that my question is going to make sense, but I will try anyway. So I was just wondering, I'm doing kernels on manifolds, and but there is this overarching story there that if you start from distances, you get in deep trouble usually, but you can get around this by starting differently and you working, for example, with the heat kernel and its relatives. So here, when you talked about scoring rules, just in the first part, everything seemed to be still induced by distances. Can you win something if you also, I don't know, use heat kernel or something like this to define the scoring rules?
If you use a heat kernel, you're not guaranteed for the corresponding scoring rule to be strictly proper. You might get propriety, but if you want strict propriety, as you do get with
so
the energy score,
that you will not get strict.
You needn't. It depends on the manifold. It's not always the case.
Okay. And do you have any ideas about like practical behavior? So the fact that it's not strict proper, it's sort of ruling out this direction for us, or.
So I'm not an expert in this, but from what I do understand, if you want to use a scoring rule for estimation, for instance, if you don't have strict propriety, then you probably won't have unique minimizer, and hence consistency with increasing sample size as well.
Back to David's question, for estimating the score using Markov chain Monte Carlo, aren't you just better off running two independent Markov chains?
Yeah, you can. In fact, you can construct an estimator running many chains independently. No need to run for that long, and then take an estimator based on averages of averages. That's also there. To do that as well.
Good. Let's thank our speaker.